Hello, so these are my solutions to the Breadth in Physics paper from 2018, and this is for OCR Specification A. And on this paper, out of a total of 70 marks, you had to get 48 to get an A. But it starts with multiple choice, so let's begin with question number 1. So in question number 1, we had a graph, so it's a displacement time graph, and we wanted to look at the point where it has maximum velocity. So if it's going to have maximum velocity, that must mean it must have the steepest gradient. So that's why region B must be the point where it's travelling fastest. So for this one, the answer is B. Okay, so for question 2, we want to use something which is using quantities rather than units. So reading the first one, acceleration is a change in velocity per second. Well, second is a unit. So velocity is a quantity, second is something that something's measured in, so it can't be the first one. And equally the second one, we've got something per ampere, so that's using units as well. The next one, we've got intensity as energy per cross-sectional area, so that's all quantities. And so is the last one about electromotive force being the energy per unit charge. But intensity, it says it's the energy per unit cross-sectional area. That is the incorrect bit of physics. Intensity would be the power per cross-sectional area, so it would be the energy per second. So it can't be C, and that's why the answer is D. For number 3, maybe a little bit tricky. What we have is the ball at point X, and we want to know which is the resultant force on it. So if we think about X, what's going on? Well, there's going to be a weight force which is acting down. So we've got a downwards arrow. And it says as well that the ball experiences a small amount of drag compared to its weight. Now, at this point, the ball is going to be travelling in this direction. So that's the direction it's going. So that must mean there must be a drag force which is acting in the opposite direction to its motion. So this is going to be the drag force here, and that size of that drag is going to be small compared to the weight. So if we want to look at the resultant of these two forces, that's a bit like having an arrow down and an arrow to the side, and that means we're going to have a resultant force in this direction. So that means B is the most appropriate answer. It can't be C, because that would just be the force if there's no drag. A would be more like if the drag force was really big, and it definitely can't be D, so B has to be the right answer. Right, the next one, number 4. Even though this is a multiple choice question, you can still show you're working out. So we've got, I'm just going to do this as a diagram. So this is going to be object P here, and it's travelling to the right, and I'm just going to put an arrow above it to show it's travelling to the right, and its momentum is 40 kilogram meters per second. And it travels with another object Q travelling to the left with the same path. So here's object Q. We don't know its momentum, but we do know that after the collision, the momentum is going to be smaller, and now it's a value of 10 to the right. Now we don't know what's happened to Q. It could have bounced back. It could have joined up and been moving off together. But we want to know the change in momentum of Q. Now, if we think about object P, the change in momentum of object P is going to be equal to 40, which was its initial momentum, take away 10, which is its final momentum, and therefore its change in momentum would be 30 kilogram meters per second. But in this collision here, we're going to assume that momentum is conserved in this collision. There's no external forces acting, and that means if the momentum of P goes down by 30, that means the momentum of Q, so the change in momentum of Q, must also be equal to 30, so that momentum is conserved, and that's the reason why C is going to be the correct answer. Okay, so whatever the change in momentum of P is, that's going to be equal to the change in momentum of Q. Okay, so now we've got a question about resistivity. So it says wire P has a length L, diameter D, and a resistance of 1 ohm. And then we've got another wire Q. So same metal, so that means it must have the same resistivity, but now it's got 3 times the length and double the diameter. So I'm just going to write down the equation that says resistance is equal to the resistivity times the length divided by the area. Okay, so what we can infer from this is that if you've got something which is 3 times the length, so say we've got this extra wire which is Q, because its length is 3 times as long, that means its resistance is going to be 3 times as big. The other thing about it is if it's got diameter 2d, you've got to remember, of course, that area is equal to pi d squared over 4. And that means if you double the diameter, that means the area, so let's say, so we've got 2 times the diameter, that means the area is going to go up by a factor of 4. Okay, so now if we want to look at the resistance of this other wire, we can say the resistance is going to be equal to, it's going to be, the resistivity is going to be the same. We're going to have 3 times the length, but now we've got 4 times the area. Okay, and provided these are all constants, so the values of rho and so on like that, that means the resistance is going to be equal to 3/4 of the initial resistance. So the resistance of P here, and this is the resistance of Q, we can say that the resistance of Q is going to be equal to 3/4 of the resistance of wire P. And initially it was 1, but now we're going to have 3/4 of that, so the answer is going to be A, which is 0.75. For question 6, I'm just going to write down some information onto the diagram. So it says that the power of lamp X is 2 watts. So this has got a value of 2.0 watts, and Y has a power of 6.0 watts. Okay, now for this circuit here, because it's a series circuit, I is going to be constant or the same in every part of that circuit. And we also know, of course, that P is equal to I times V. So if we know the power, we can look at the potential difference. Now for this circuit, because I is going to be a constant, we can say that the power is going to be proportional to the potential difference. So the potential difference of this is going to be 1/3 of the potential difference across Y. So we've got to think about how we've got 2 to 6, how that ratio, links to how that potential difference is shared. And if 2 and 6 are 8, and we've got 16 there, effectively we can then, just imagine that that's going to be equal to 4.0 volts there and 12.0 volts there. Okay, so this one here is going to be taking 3/4 of that potential difference, leaving 1/4 of the potential difference across component X. So the PD across X is going to be 4 volts, and that's why the answer is B. For question 7, we've got 2 resistors, and everything's labelled on the diagram, which is quite nice. We've got a 2 ohm and a 4 ohm resistor. We've got an EMF of 1.4 volts with the internal resistance of 1 ohm. So let's think about how much of the share of this 1.4 volts each of these components has. Now, in total, I suppose we can say that the total resistance of everything here is going to be equal to 1 plus 2 plus 4. So the total resistance is going to be equal to 7.0 ohms, and we're interested in how much of a share this 2 ohm resistor has. Well, that's going to be 2 ohms over the total resistance, which is going to be 7. So effectively what we're saying is that this 2 ohm resistor has 2/7 of the total resistance of everything, and that means it's also going to have 2/7 of the total EMF across it. So we're thinking about what's going to be the potential difference across this component. Well, effectively it's going to be 2/7 of 1.4. Okay, so we can just probably put this number into our calculator. Well, actually we don't even really need to do that, because this is the same as 2.8 over 7, which is just going to be equal to 0.40. So for this one over here, for answer 7, the answer is going to be A, which is 0.4 volts. For question 8, I'm going to look at the percentage uncertainty in I and the percentage uncertainty in R. So first of all, for I, the percentage uncertainty is going to be the uncertainty, so 0.2 over the measured value of 4.0, and I'm going to multiply this by 100. So 0.2 divided by 4 times 100 is going to be equal to 5.0%. The uncertainty in R is going to be equal to 0.3 over 3, again multiplied by 100, which is just equal to 10%. Now, it says that P is equal to I squared R. So to work out the uncertainty in P, it's going to be equal to the uncertainty in I, which is 5.0. But we've got I squared, so we're going to add the uncertainty in I again. And then we've got 1 times the uncertainty in R, so that's plus 10%. So the uncertainty in P is going to be 5 plus 5 plus 10, which is 20. So that's why the answer is B. For question 9, I think this was a bit of a tricky one for many students. Maybe we can just label a diagram here. So we're going to have a force acting down at the centre of the rod because it's a uniform rod, and that's going to be equal to the weight. And we've also got a tension acting in the cable up here. Now, in terms of up and down, the weight of the rod is equal to the vertical component of tension acting upwards, but that means there's going to be effectively a force to the left. So there must be something acting to the right. And if we think about maybe drawing a triangle of forces, we've got the weight acting down, we've got the tension acting at an angle here, and that means there must be another force acting to the right. And that force is provided by the kind of force that's X here. So that's why for this one here, the answer is C, because there must be a horizontal force acting to the right that counteracts the weight acting down and the tension acting up at this angle. So 9, the answer is C. So for question 10, we've got a velocity time graph. As some data on here, but it doesn't give us the size of the velocity initially. But it does say the thinking distance is 10 meters. Now the thinking distance is going to be equal to this part of the graph. Okay, and that's because that's the region before the car starts to slow down. So this distance here must be equal to 10 meters, and the area underneath the velocity time graph is equal to that displacement. Now, this, if that's 1, this is going to be equal to 0.5. So 0.5 times something is equal to 10, and that's why the initial velocity must be equal to 20 meters per second, because this area is equal to 10. But we want to know the stopping distance of the car, and the stopping distance is going to be equal to the thinking plus the braking distance, so it's going to be equal to the total area under the line. So we know that that area is 10 meters. We now need to work out this area in here. And that's going to be equal to half of the base times the height. So the base goes from 0.5 to 2.5, so that's 2.0. And the height goes from 0 to 20. So we've got 2 times 20, which is 40, divided by 2 is equal to 20. So the total stopping distance must be equal to the initial thinking distance of 10 plus the braking distance of 20. And that's why for this one, the answer is B. For number 11, we've got loads of data. So there's a javelin thrower, there's a force exerted of 100 newtons for this time, and it has this mass. What is the rate of change of the momentum of the javelin? So for this one here, it might be worth just remembering that the definition of Newton's second law is that the force is equal to the rate of change of momentum. So here, the rate of change of momentum, which is what we're trying to find out, must be equal to the force, which is this number up here. We don't really mind how long it acts for. We don't really care about the mass of the javelin. We're just wanting to know effectively the force. And here that's going to be 100 newtons, and that means the rate of change of momentum of the javelin must be 100 kilogram meters per second squared. So that's why for this one here, the answer is C. So effectively, ignore that data, ignore the fact it's a javelin, and this force is going to be equal to that rate of change of momentum. So we've got some material stuff here. We've got a wire, so maybe just draw a diagram. So this is a wire. It's got an object which has a mass of 3.0 kilograms. On the end, it's got this diameter of 0.62 millimeters, and effectively the mass of the wire is negligible. What's the stress in the wire? So the stress is going to be equal to the force per unit area. Now the force is going to be equal to the weight, and that's going to be equal to 3 kilograms times 9.81. The area is going to be equal to pi r squared. So you could do pi d squared over 4. Let's just do pi r squared. So we've got pi times the radius, which is 0.31 times 10 to the minus 3. So converting from millimeters to meters, and that's going to be squared. Okay, so this one here, I'm not even looking at the answers yet. I'm just going to go straight for, this is the calculation I'm going to use, and then I'm going to see if that answer comes up with one of these. And this gives me an answer of 974. So this is equal to 9.748 times 10 to the 7, and that would be pascals. So over here, to two significant figures, probably like our raw data, we would say that's equal to 9.7, and D just happens to be the right answer. So for this one here, we're just using the equation that stress is force over area. We've identified the force acting on the wire, which is caused by the weight of that object. We've worked out the area, so we're not using the diameter directly, we're using this to work out the area to give that answer. Okay, the next one is about the light intensity on a light-dependent resistor. So why, for an LDR, does the resistance decrease when we shine more light on it? Well, the cross-section doesn't change. The magnitude of the charge and the charge carriers increases isn't true. They don't get quicker, but what happens is that the number density, N, gets bigger. So we shine light on it, more charge carriers are released, and therefore there's more of them in that material. So that's why C is the correct answer. And for 14, we've now got 20 electrons travelling through a PD, where the V is 30 kiloelectron volts. What is the potential difference V? So what we're looking at is, if we've got 30,000 electron volts divided by 20 things, that means we're going to have 30,000 divided by 20, giving an answer equal to 1,500 electron volts. So that's the amount of energy gained by each electron. And that means, because if one electron is accelerated through a PD of 1 volt, it has 1 electron volt of energy. But if it's going to get this much energy, say 1,500 electron volts, then it must be going through a PD of 1,500 volts. Okay, and so for that reason, C is the right answer. So for 15, I'm going to be using this space just to draw a diagram and do some calculations. So this is a trolley of mass 1 kilogram, and initially it's moving at a velocity equal to 2 meters per second. So the mass is equal to 1.0. So that means its momentum initially is going to be equal to its mass times velocity. So that's equal to 1 times 2, which equals 2.0 kilogram meters per second in this direction. Okay. After that, there's going to be a force acting on it, and it says that the force of 3 newtons acts for a time of 1.5 seconds. Now, the force multiplied by time is going to be equal to its change in momentum. Okay, so its change in momentum is going to be equal to the force of 3.0 times the time of 1.5, and that's going to be equal to 4.5 kilogram meters per second. Now we can give this in Newton seconds because this is the impulse, or we can give it in kilogram meters per second because that's also then going to be the units of change in momentum. But the thing is, this force is going to be acting in this direction, and therefore this is going to be a negative value. So this is going to be a value of minus 4.5 kilogram meters per second. So what's the change? Well, it was going at 2.0. We're going to take away 4.5, and that's going to be equal to a final momentum of the trolley of minus 2.5 kilogram meter second to the minus 1. But we want to know the magnitude. So the magnitude of this, the size of that, is going to be equal to 2.5 kilogram meters per second, and that's why the answer is B. For 16, we've got the current at a point on the circuit is 10 milliamps, and to the nearest power of 10, how many electrons pass the point in 10 seconds? So the charge transferred is going to be equal to IT, and that's going to be 10 times 10 to the minus 3 for the current, multiplied by the time of 10. So 10 times 10 to the minus 3 times 10 is equal to 0.10 coulombs. Now, the charge transferred is going to be equal to the number of electrons times the elementary charge on each electron, and therefore the number of electrons is going to be the total charge divided by the charge per electron. So that's going to be 0.10 divided by 1.6 times 10 to the minus 19. And that's equal to 6.25 times 10 to the 17 electrons. Okay, so we're looking in the order of 10 to the 17, but effectively this is closer to 10 than it is to 1. So that's equivalent to about, something in the order of 10 to the 18. And that's why for this one, the answer is C. And for number 17, we're looking at EM radiation incident on a metal plate. And effectively what we can remember is that the energy of that photon is going to be equal to the work function plus the maximum kinetic energy of the photoelectrons emitted. So if we look at the instant energy is 5 electron volts, that's going to be equal to the work function of 3.0 electron volts plus the potential maximum kinetic energy. So that means K max must be equal to 2.0. So that means any photoelectrons can't have any energy bigger than 2 electron volts, and that's why D can't be right. And so the correct answer, so which of these is the wrong answer, must be D. So 17, the answer is D. For 18, we're looking at what is really the definition of coherent wave sources, and these are sources which have a constant phase difference. So 18, the answer is D, and that relies on you knowing about what coherence means and just remembering that definition. The next one is about a stationary wave. So this is in a tube with one open end and a closed end. And we know that this length is equal to 60 centimetres. Now what I can see immediately, if you've effectively got a node, an antinode and a node, and you've got to remember that the distance from a node to a node is equal to half the wavelength. So this distance here is going to be equal to half the wavelength. And if that's 60, this distance must be equal to 40 centimetres. So half the wavelength is 40, and that means the complete wavelength would be 80 centimetres. And that's why for 19, the answer is D. And the next one, which are the correct base units for work done or energy? Now, the way I'm going to approach this, because I can't remember, is that energy, or the potential energy, for example, is equal to mgh. And if I can remember the units for these three things, I can work out the units for energy. So mass, it has got the units of kilogram. The gravitational field strength has units of newtons per kilogram, but this can also be expressed in meters per second squared. So it's ms to the minus 2. And height is a distance, so it has the units of meters. So these are the three units we're going to combine together. We've got kilograms, we've got meters, and we've got meters, so that's going to be meters squared, and we've got s to the minus 2. And so I've done that first of all, and then checking down here, it can't be this, this, or this. So again, for this one here, the answer must be D. So we can also express the units of joules in kilogram meters squared second to the minus 2. So that's the end of the multiple choice, and actually I thought they were generally quite nice. So now we've got some of the kind of more standard style exam questions. So the first one, we've got a trolley on a ramp, and actually there's a picture of it down here. And it says it has a constant acceleration, so it must be this kind of nice straight ramp that we have here. How could a meter rule and a stopwatch be used to determine the final velocity v of the trolley at the bottom of the ramp? So what we want to be doing is we use the, I suppose we use a meter rule to measure the distance. I mean, I tend to call it a ruler rather than a rule, but so we're using the ruler to measure the total distance, and then we're going to be using the stopwatch to measure the total time. And if we know the total distance and the total time, we can use these to calculate the average velocity. So that's kind of what gets you the first mark, so very straightforward. But the final velocity is going to be equal to double the average velocity, because effectively it starts at 0. If it's constant acceleration, its average velocity is going to be half the final velocity. So we can use this average velocity to work out the final velocity. So I think most of you will have got the marks for part A. Part B, we're now going to be looking at some kind of Suvat equation. So we've got the trolley, we've got a distance here, and we've got at x, it says the velocity is 1.3, and at y, the velocity is 2.5. So if it's a SUVAT kind of style question, I'm just going to write down SUVAT. We know the distance travelled is 1.10 metres. The initial velocity is going to be the one at x, so that's equal to 1.3 metres per second. The final velocity is 2.5 metres per second. And we want to calculate the acceleration, so this is our unknown. So the equation that links these together is that v squared is equal to u squared plus 2as. I'm going to rearrange this to make a the subject, so I'm going to have v squared minus u squared, divide this by 2s, and that's going to be equal to a. So now we just put the numbers in. So a is going to be equal to 2.5 squared, take away 1.3 squared, over 2 times 1.10. And this gives me an answer of 2.07. So to two significant figures, like this raw data here of 1.3, I'm going to give that to two significant figures. So 2.07 is going to be equal to 2.1 metres per second squared. Now it says there are no frictional forces acting on the trolley, and this is the acceleration down the trolley is equal to the component of the acceleration of free fall parallel to the ramp. So we're going to work out the angle between the ramp and the horizontal. So here's my quick diagram. So this is going to be the trolley. Now there's going to be a force down, which is due to the weight of that trolley, which is equal to mg. Okay, now this is going to be going down the slope. Okay, so this is my kind of picture of the slope, and it's going to make an angle of theta to the horizontal, which is what we're trying to find out. So that's the angle between the ramp and the horizontal. Now, if that angle is theta, if we kind of draw another line up here, what we find is that this angle here is also equal to theta. Okay, and we're trying to find out effectively the component of the force which is acting down the ramp, because there's going to be this component of force acting in this direction which is causing that acceleration down the ramp. Now if we know that we've got theta here and that size is equal to mg, we can say that this length is going to be equal, so this is the force causing the acceleration, that's going to be equal to mg sine theta, because effectively that's the hypotenuse and that's the opposite side. So the component of weight, so the force that's causing to accelerate down the slope, is equal to mg sine theta. But this force is also going to cause the acceleration, so that force is going to cause the mass of that trolley to accelerate, so F equals ma. So what we can then say is that this component, mg sine theta, is equal to ma. The m's cancel, and what we can then say is that g sine theta is equal to a, and we can rearrange this to make theta the subject. So theta is going to be equal to a over g, and we're going to do inverse sine of that. Now, in the last part of the question, we found out the acceleration down the ramp, and we also know the gravitational field strength. So that means theta must be equal to sine to the minus 1 of 2.07 over 9.81. So I've still got the answer saved on my calculator from the previous step. Divide by 9.81, and we're going to do inverse sine of that to get an answer of theta equal to 12.2. So here, theta must be equal to 12 degrees. Okay, to two significant figures. So figure 22 has a lot of information. It's got quite a nice diagram, and we've got this object of weight W, which is supported by two identical springs which are acting up here. So we want to state and explain the magnitude and direction of the resultant force at x due to the two forces exerted by the extended springs. Okay, so what we're saying is that there must be a force here and a force here. What's there going to be the resultant? But it says state, and that means there must be no calculation involved. Now, effectively, because this object is in equilibrium, we can say that the downwards forces are equal to the upwards forces. And that means the downwards force is equal to W, which is 4.8. So the magnitude of that resultant force up must be equal to the size of that force down. So the force is going to be equal to 4.8 newtons, and that's going to be upwards. So we stated the magnitude and direction. We can explain it now because the object is in equilibrium. and therefore there must be balanced forces acting on it. So using this information, this is going to help us when we draw a triangle of forces. We're going to draw it with a ruler. So first of all, I'm going to do a downwards force, which is going to be due to the weight of the object. So that's going to be equal to my 4.8 newtons. Now, there must be a tension. Effectively, there's going to be one tension this way and one tension that way. So we can go left and then right, or right and left. I'm going to go this way. And actually what I'm going to do is I'm just going to use kind of the end of my ruler to kind of sort of line this up, because the angle between this tension and that tension must be equal to 90 degrees. So I'm going to do it something like that. So this is again just my kind of sort of scale drawing. Let's see, it's something a bit like this. Okay, now it's not the best, but I think it's quite clear, especially when I label this as a tension and this as a tension. And the other thing we're going to do is just put in a right angle here. And also, if that's the right angle and these are the same length, then this angle must be 45 degrees and that angle must be 45 degrees as well. So don't forget to label the angles. So what we have now is a labelled triangle of forces showing that effectively T here and T there are equal to the size of W, which is acting down. Now part C is a show me question, which is quite nice because it gives us the answer that we're aiming for, and we want to find out the value of the tension. Now actually we're going to use this triangle here because what we have is a right angled triangle and these two sides are the same length, T, and we've got a known value for W, which is 4.8 newtons. So we can use Pythagoras because we know that this squared plus this squared make that squared. So what we can say is that 4.8 squared is equal to T squared plus T squared. And that means that T must be equal to 4.8 squared over 2 square rooted. So we don't even need to use sine or cos or anything. We can just go straight to Pythagoras. So 4.8 squared divided by 2 square rooted gives me an answer of 3.39. Now, it's important in a show me question that you show your answer to more significant figures than they've given you in the question. So if I just put this is equal to 3.4, that doesn't actually prove I've done that calculation. So 3.39, which is about 3.4 newtons. And then the last one. The force constant of each spring is 24 newtons per metre. Calculate the energy stored. Now we know the force in these things, so we know that the force is equal to 3.39. We know that K is equal to 24. And from our data sheet, we can see that not only is F equal to Kx, but also the energy stored is equal to a half Fx. Now, we could do something where we actually work out the extension of those springs, but we could say that X is equal to the force over K, and then we can substitute this back into this equation up here to say that the energy stored is equal to a half times the force times X, and X is equal to F over K. So the energy stored is actually equal to F squared over 2K. And that means I know these values immediately, so I can say that's equal to this value of 3.39 squared divided by 2 times 24. So again, I've got this number saved on my calculator. I'm going to square that, divide it by 48 to find the answer of the energy is equal to 0.24 joules. Okay, and that's the energy stored in each spring. So for question 23, there's a lot of information. So we've got this container, we've got a sealed hollow tube, and then the water level is increasing. And we've also got the force on the string. So this is the tension, and that's going to be increasing as the thing is kind of filled up with water. So lots of information there. The first part says, by considering the forces acting on the tube, explain the shape of the graph shown in figure 23.2. So let's think about the forces acting on the tube. Well, we've got the upthrust. Now, you can call this buoyancy, but you've got to make sure that you call it the buoyancy force. Buoyancy on its own isn't good enough. There's going to be an upthrust. There's also going to be the weight. And there's going to be that force in the string. which is going to be equal to the tension. Okay, so it's going to be the tension which is labelled F on that graph. And if we think about what's going on, you've got the, so this is my sealed hollow tube. We're going to have the weight acting down, which is going to be a constant. There's going to be this value of F acting down as well. And there's also going to be an upthrust as well. So this upthrust is going to be in this upwards direction, as the name I guess implies, and there's going to be a weight acting down, and also this value of F is going to be acting down as well. So what can we say about what's going on? Basically, we can say that the upthrust must be equal to the weight plus the force or the tension in that string. Okay, and this is because that sealed hollow tube is going to be static, so at all times there must be balanced forces acting on it. But what we can see is that as the water level rises, the force must increase in that string because the upthrust is increasing as well. So basically what we can say is that the force increases, and that means the upthrust increases until the tube is fully submerged. So what we're doing here is really describing the shape of that graph. So the force increases and the upthrust increases until the tube is fully submerged. Why does the upthrust increase? Well, what we could talk about, because the upthrust increases because the weight of water displaced increases until it gets this maximum value when it's fully submerged. So you got marks in this question for maybe identifying the different forces. So upthrust, don't forget the weight of that tube and the tension in that string. For maybe looking at how these are linked together, how the upthrust is equal to the weight plus that force. And then we can talk about why what's actually happening. And it's because the upthrust is increasing because the weight of the water displaced inside that container increases as well. So that was 23 part A. We've now got the container's now full of water. The string is cut and the tube accelerates vertically upwards through the water. So what we've got now is there's going to be an upthrust acting up and there's going to be a weight acting down, but there's no force holding it down, and that means the force up is bigger than the force down and there's going to be a resultant force upwards. So it says here that the upthrust is 4.2 newtons, the weight of the tube is 0.80, and that means the resultant force is just going to be equal to 4.2 take away 0.80, which is 3.4 newtons. So that's going to be the resultant force upwards. We know, of course, that F equals ma, and we're trying to find the acceleration. So A is equal to F over m. The resultant force is 3.4. What about the mass of the tube? Well, it says the weight of the tube is equal to 0.80 newtons, and we know that mass is equal to its weight divided by the gravitational field strength. So that's equal to 0.80 divided by 9.81 to convert from its weight in newtons to its mass in kilograms. So this then gives an answer equal to 41.69. So I'm going to say this then is equal to 42 meters per second squared to two significant figures like the raw data. So for this one here, we're just using this case of Newton's second law to find out its initial upwards acceleration. We've worked out the resultant force, we've worked out the mass, and we've used that to work out the acceleration. But as the tube goes higher and higher, the acceleration decreases. Now it's still going to be a positive value of acceleration, but it's not going to stay at 42 meters per second squared. So why could that be? Well, what we might say is that the drag increases, because if it's going through water, it's quite a viscous thing, and as it's going faster and faster, there's going to be a bigger drag force. So that means not only is there weight acting against it, there's also going to be the drag acting against the upthrust, which is upwards. So we can say that the drag increases as it moves through the water. So that was the end of question 23. So question 24 has some data about V and I for this unknown component. It says the PD across a component is V and the current through it is I, and we want to know the power dissipated when V is equal to plus 10 volts. Now, this one here, we're just going to use the equation that says P is equal to I times V. and that's going to be equal to the value of I, which is 30.0, but it's in milliamps here. So that's times 10 to the minus 3. We're going to multiply that by the potential difference, which is 10.0. So this is a fairly straightforward calculation, which is why it's only 1 mark. So we've got 30 times 10 to the minus 3 times 10, giving an answer equal to 0.300. So the power is 0.300 watts. I've given that to 3 significant figures as well, like the data over here. So a nice straightforward bit to begin with. We're then going to analyse the data in the table and identify the component. So I guess to maybe really work out which component it might be, we maybe need to think about its kind of IV characteristics. So what happens to the resistance at different times? So in the table, I'm just going to put my other column of R, and effectively R, because R is equal to V over I, I'm just going to work out values over here. So the first one, we've got 5 volts divided by 5 times 10 to the minus 3 amps. So that's going to have a resistance of 1000. The second one, well, we've just got positive values because those were negative divided by negative numbers. Now we've got positive divided by positive, which will also be 1000. And then this one here, we've got something which is 10 divided by 30 times 10 to the minus 3, which is equal to 333. So what we can see is that the resistance decreases when we have a higher potential difference and a higher current. Now that's kind of the opposite to most components. Most things, when you've got a higher current, their resistance increases. So filament lamps, their resistance increases. It can't be like a resistor, because that would then have a constant resistance. So this is something where the resistance decreases. And I guess what we can say is that as the potential difference and the current increase, the resistance decreases. Okay, so that's what we've found from analysing the data. And therefore the component could be a thermistor. So this is something where when it gets hotter, the resistance goes down. And so that's the component that I've suggested. And I'm going to give a reason about why it would be that. So we might say that a higher current causes a heating effect, and this then lowers its resistance. So again, we're thinking about the kind of curve that looks like this. When you've got something which gets hotter, then its resistance goes down. So for this one here, we've analysed the data, found that the resistance gets smaller, and therefore it could be a thermistor, because when you've got a greater current, we have more of a heating effect. It increases the temperature, and that means the resistance decreases. We now have a nice simple circuit. So we've got the battery here, we've got 2 resistors. It says there's some information about X, which we'll come on to in a sec. There's no internal resistance, and resistor Y has a resistance of 68 ohms. Okay, but we don't know the value of resistor X. But we do know that R is equal to rho L over A. So we can, if we know its resistivity, the length and the area, we can find out this value. Now, it does say that the value of the resistivity is 1.5 times 10 to the minus 2. The length is quite small, so 8.0 times 10 to the minus 3, so about 8 millimeters long. And we're going to divide this by the area. Now it says the area is 1.2 millimeters squared. We need to convert from millimeters squared into square meters. And effectively, because you've got 10 to the minus 3 squared, this is going to be by 10 to the minus 6. So a common mistake that lots of people did, they just put 1.2 times 10 to the minus 3. They didn't convert it from millimeters to meters squared. So we're going to put the numbers into the calculator, so 1.5. And this comes out at a lovely number equal to 100. Now, the total resistance is going to be equal to the resistance of X plus the resistance of Y, because these two things are in series with one another. So that's just going to be equal to 100, the number we've worked out here, plus the number given to us as 68. So that's equal to 168 ohms in total. And I is going to be equal to V over RT. So that's equal to 3.0 divided by 168, which equals 0.01786. So that's going to be equal to 0.018 amps. So this one here, we just had to use the equation for resistivity to work out the resistance of this resistor, add it to this, and then we use this equation here to find out the total current is 0.018 amps. Now, lots of students really struggled with 25A trying to get the 2 marks, and I think it's just because setting up oscilloscopes is actually quite difficult to do in practice. But the question is, how can the trace on the screen be used to determine the frequency of the sound waves? Now, effectively what you get is, this is your sound wave on the screen, and there's going to be the kind of the background to the oscilloscope here, and what you have is something that looks at effectively the voltage up here, that's the Y gain, and then across the x-axis, what it's doing, it's measuring the time base. Okay, now what you can do on the oscilloscope is you can adjust the time base till you get one wave, and then what you can do is you can count from one peak to another peak, or maybe a trough to a trough, and also you can adjust this up and down, so it's all, there's a lot of control that you have over an oscilloscope. And effectively what you're going to be doing is you're going to be adjusting the time base to get one complete wave trace on the screen. And what you can then do is you can measure the time period t, and you can do that by reading it off this. But to work out the frequency is going to be equal to 1 divided by this time period. And that's important. With an oscilloscope, you don't measure the frequency directly, you can only measure the time for one wave, and then once you know that time period, you can then use that to work out the frequency. So, most people got this mark here, but they were a bit unclear about how you actually found the time period for maybe counting the squares, or actually looking at the scale on the side of the oscilloscope to actually work that out. So 25A, if you do get the chance in school, have a play with an oscilloscope. It's going to be frustrating, but it's just good to get hands-on experience with it. Now for part B, there was a huge amount of information. We had graphs over here. There's information about the loudspeaker from the previous page. So this takes a while to actually try and work out what they're asking for. But first of all, on figure 25.3, so this one here, draw the variation of x with time t at point P. Now, it says that the sound from L2 at point B has an amplitude of 1 micrometers, so we're going to have an amplitude of either +1 or -1. It's got a phase difference of 180 degrees, but it's got the same frequency. Now, if it's got the same frequency, then it's going to be the same value here at 0, 5, 10, and 15. But if it's got a phase difference of 180 degrees, when this one's a peak, this one's going to be a trough. So I'm just going to put in my kind of other values, and hopefully that's going to help me draw the wave trace. Now the other thing you can do is you can move your exam paper around, and that might make it easier when it comes to actually drawing the shapes that we're trying to draw. So it's always easier to draw your curves away from you. So hopefully this is the kind of thing you can do. So actually, I'm pretty pleased with that. That looks pretty good, doesn't it? So this one here, again, the bits they're going to be marking you for are the fact it goes down, up, down. It's got the same frequency, but now it goes up to a value of 1. So this one here is one straightforward mark. So what we're doing is looking at how this value varies with time. For part 2 though, we're going to look at the intensity of P due to the sound from both L1 and L2. But it's not the same as the intensity from L1. So effectively, this is what happens if we were to look at the amplitude of the signal just from one speaker. But if you've got 2 speakers, this one here is also contributing to that final sound. Now, basically what we find is that the amplitude is smaller when you've got both L1 and L2. And that's because effectively you've got a positive amplitude here at the same time as we've got a negative amplitude here. So we're going to get some destructive interference. So the amplitude is smaller when you've got 2 sounds, and that means that the intensity of that sound is going to be smaller as well, because we can say that the intensity is proportional to the amplitude squared. So when you've got a smaller amplitude, we're going to have a smaller intensity. In actual fact, the intensity, because the amplitude, it was going up to 3, now it's going to be equal to 3 take away 1, so now it's going to 2. So what we can say is that the amplitude is now equal to 2/3 of the original value, and that means the intensity, which is proportional to a squared, is going to be equal to 4/9. So effectively, the intensity is now 4/9 of its original value, so basically half as loud as it was before. And I suppose the last part, part 3, it says the wavelength of the sound is 34 centimetres. The distance from L1 to Q is 200, and the distance L2 to Q is 217. So that means the path difference, so the difference in the distance that these two waves have travelled is equal to 217 take away 200, which equals 17 centimetres. But that is equal to half the wavelength. And when you've got a path difference equal to half the wavelength, that's when we get complete destructive interference, or the maximum destructive interference. So we can say the path difference is equal to lambda over 2, and that means we get destructive interference. And I think for this question here, loads of students realised it was destructive, but I guess this is justifying why that is, because the path difference is equal to half the wavelength of that sound. So 26, we've got a microwave transmitter, we've got a receiver and a kind of a large slit. You might have had to go with some of this stuff in your lab at school anyway, so hopefully you've been used to using these microwave transmitters. The first one, we want to know the wavelength of the microwaves. So we can say that C is equal to F lambda, and because they're microwaves, it means they must travel at the speed of light, so 3 times 10 to the 8. We want to work out the wavelength. So that's going to be equal to the speed of light divided by the frequency. You should remember this is 3.0 times 10 to the 8, or you can always look up the data in your data book. And the frequency is 11 times 10 to the 9, because it's gigahertz. So this one here then, so 3 times 10 to the 8 divided by 11, 10 to the 9, gives an answer of 0.0272727. So the wavelength is 0.027 meters, and I think that that's about kind of roughly about 3 centimeters, which is the wavelength of the microwaves that we get from the transmitters we have in school. Now we've then got so basically initially the receiver didn't receive anything, but when you put the slits together there's going to be a smaller gap or aperture, and what we now have is a receiver picking something up. So the receiver now detects microwaves, and the reason for this is because of diffraction. And the reason we get diffraction here is because the wavelength is approximately equal in size to the gap. So if we think about what's happening, we've got the wavelength is a bit like this. That's about a similar size to the gap. And what we then get is maximum diffraction to the receiver. Okay, so we've got diffraction happening, and this happens when the wavelength is approximately equal to the gap or the aperture, and that's when you get maximum diffraction occurring. The question now moves on to light travelling from air to water. So if it's going from air to water, it's going to slow down, and we want to kind of look at the speed, frequency and wavelength of the light in air and in water. So I'm just going to say that V is equal to F lambda. So that's the wave speed equation we use all the time. Now the key thing to remember is that the frequency stays the same. So there'll always be the same number of wave fronts passing a point every second. So the frequency stays the same, so that's going to be a fixed value, but the value for the speed decreases. And we can say the speed decreases in the water. So it slows down because it's now going through a denser, optically denser medium. Now if that's the same and that value gets lower, then that means the value for the lambda must also get lower as well. So we can also say that the wavelength decreases. And that's it, that's your 3 marks. So what we're doing is we're comparing the speed, frequency and wavelength of the light in air and water. So frequency stays the same, speed decreases in the water and the wavelength decreases in the water. Now, the next question was actually relatively straightforward, but I think a lot of students lost marks because they weren't actually describing how to work out the critical angle for light, and therefore the refractive index of the glass. So what we're looking at doing is we're looking at maybe the central point of this semicircular glass block, and what we're going to be doing is we're going to be sending a ray of light towards this. So I'm just going to put a dotted line here, which is my normal, and we're going to have a ray of light that comes in like this. Okay, now if we're directing that ray of light through the side here, there's going to be 0 angle of incidence, so it just goes straight through. And what we're going to be doing here is we can measure the angle of incidence here, And then we can also, I suppose, look at the angle of refraction. And what we're interested in is the point when the light doesn't escape the block. And effectively, the ray of light travels in this direction along the surface, and effectively that's where the angle of refraction, I suppose effectively, is 90 degrees. So what do we need? Well, we need some equipment. So you might think about having a ray box or a laser source perhaps. So you've got to outline exactly which equipment you're going to be using. So you're going to be using a ray box. You're also going to be using a protractor in order to measure the angle. So these basic things, don't forget to include them in your answer. And what you're going to be doing is you're going to be increasing the angle of incidence, and we're going to be doing this until the light doesn't escape. So we increase the angle of incidence until the light doesn't escape but travels along the straight edge of the block. And what we can then say is that this angle I is now the critical angle. And to work out the refractive index, we can say that n is equal to 1 over sine c. So we can work out this angle here, the critical angle. At that point, no light is escaping, and beyond that critical angle, we're going to get total internal reflection. And that means we can then say that the refractive index is equal to 1 over sine c. So for this question here, we're not looking at lots of values of sine I and sine r. We're using this to determine the critical angle for light within the blocks, and if you know that critical angle, we can then look at the refractive index of that glass. So that was the answer for part C. Generally, I think people maybe talked about other experiments with maybe a rectangular block where they were just looking at sine I and sine r, but for this one here, it was all about trying to work out the value for that critical angle. Now, just because this was the last question on the paper doesn't mean it was the hardest. So 27, we've just got radio waves and X-rays, both sorts of EM waves. One difference between them, one difference could be the wavelength, or you could say the frequency. So lots of differences we can talk about. We've then got some information about a star, and we've got the radius, we've got the power output, we've got the wavelength. We want to show the surface intensity of the radiation is about 1.1 times 10 to the 8 watts per square metre. Now, intensity is going to be equal to the power per unit area, and the area is going to be equal to pi r squared. Well, actually, that's the surface area of a circle. If it's a sphere, we're going to be looking at 4 pi r squared. Now, you've got to remember that we've got things like 4/3 pi r cubed for the volume of a sphere. That's the surface area of a sphere, and pi r squared is the surface area of a circle. So this is even in your data book, I think, but you don't want this, you don't want this, you've got to use this value. So that means the power is going to be equal to 2.7 times 10 to the 27 watts. The area is going to be equal to 4 times pi times 1.4 times 10 to the 9 squared. Okay, so let's work this out. So this is giving me an answer equal to 1.096 times 10 to the 8, which is about 1.1 times 10 to the 8 watts per square metre. So again, because it's a show me question, I've given my answer to more significant figures than we have in the question over here. We then want to look at calculating the energy of a photon of wavelength 5 times 10 to the minus 7. Now, we can say that the energy is equal to HF, or the energy of the photon is equal to HC over lambda. So for this one here, we're going to put in some numbers. Again, you don't have to remember all of these. They're pretty much all given to you in the data book. So we've got Planck's constant, H is equal to 6.63 times 10 to the minus 34. The speed of light is 3.00 times 10 to the 8. And here it says the wavelength is equal to 5.0 times 10 to the minus 7. So we're just selecting the right equation. We're going to plug some numbers in. And this gives me an answer equal to 3.978 times 10 to the minus 19. So that's going to be to two significant figures, 4.0 times 10 to the minus 19 joules. So that one there, a relatively straightforward question. And for the very last question on the paper, we want to look at the total number of photons emitted per second from the surface of this star. Now the number is going to be equal to the energy per second, which is going to be equal to the power divided by the energy per photon, which is what we just worked out. So that's the energy per second divided by the energy per photon is going to give us the number of photons per second. So again, it gave us an answer of 2.7 times 10 to the 27 as our energy released per second. The energy of each photon is 3.978 times 10 to the minus 19 joules. And if we just divide this number by this number, we get an answer of 6.787 times 10 to the 45, so a massive number. So the number per second is 6.8 times 10 to the 45 photons per second. But massive numbers happen when you've got massive things like stars. So that was the end of the question paper for this 2018 AS paper for breadth in physics. I thought there were some generally quite nice questions there, a few tricky bits as normal, but overall I thought this was quite a good fair paper. So hopefully that's been helpful for you guys out there. If you haven't already done so, make sure that you do subscribe to me on YouTube, and also go to alevelphysicsonline.com to find so many more videos to really help you with your physics. Thank you for watching.